And so we calculated, using examples with real life numbers, we were able to calculate the probabilities for a given energy for a given energy for the subsystem 1 and subsystem 2, right? But as we talked about previously, in order for equilibrium to occur, that coincides with the state in which the entropy is maximized, right? And so, if we want to maximize our entropy, we need to find the value of U1 that maximizes the entropy. And so to find that value of U1, to find in other words, the most probable value of U1, what we're going to do is we're going to find the value of U1 that maximizes, that has the highest probability. So we can calculate max of P U1. Okay? All right, and so to calculate the energy of U1 that maximizes the probability, we would just take the derivative of that probability with respect to U1. Okay? And we know that P of U1, we defined that the probability can be described by this sort of expression. Omega 2 1 divided by omega t for all of the U1s. Okay? Alright, and if we're trying to find the maximum, then we know that this derivative we want to find when it's equal to 0. Okay? Alright, in any case, with this derivative, the denominator here, right, this is just a sort of constant value, right, because this is just for all of the U1. And since this derivative is equal to 0 and we have a constant in the bottom, that means we could factor out that constant. So this is constant. Right? So what we're really just taking the derivative of is this on top. So we'll go through and we'll perform the derivative. So we have to apply the product rule. So I'll use the star here to indicate that's the most probable value of U1. Okay. U1 star, okay, plus omega 1 U1 star d omega 2 d U1 ut minus U1 star. Okay? Alright, and I'm going to indicate that this is equal to 0, and I'm going to call this equation 1. Alright? So we have these partial derivatives of omega 1 and omega 2. Right? One thing I should point out is that we know that the total internal energy is conserved, and that's just equal to U1 plus U2. So this is a constant. So if we take the derivative of ut, that's equal to 0, and that would give us du1 plus du2. And so as a result, we know that du2 is just equal to the negative of du1. Alright, so what we could do is we could take this sort of relationship and plug it in to here. Okay? Alright, so what we get, if we go back to equation 1, is that we could rewrite the derivative like this. So now, I'm just going to plug in u2 star here. So this is omega 1 u1 star divided by d u1 minus omega 1 u1 star d omega 2 u2 star d u2, right? And so this is where I applied that relationship here, and all of that is still equal to 0. I'll rearrange the equation to combine the like terms. U1 is equal, okay? And so here, because we have the derivative over the function itself here, we could rewrite that like this. So that's the natural log. That's just from the definition of the natural log derivative. du1. And we know that this natural log of omega, based on the definition of entropy, we know that the natural log by itself is just this. Okay? We could do a similar thing with omega 2. Okay? Alright, so this one would be equal to 1 kb S2. Alright? Okay, so if we take that relationship even further, what we get is that the derivative of S1 with respect to U1 is equal to the derivative of S2 with respect to U2 star d U2. Okay? Alright, so we have this relationship now, and these derivatives should actually be familiar to you, because based on just the general properties of entropy functions, we know that the derivative of entropy with respect to the internal energy is 1 over the temperature. So that one's 1 over T1, and this one's 1 over T2. And so as a result, we find that by going through this analysis, that at equilibrium of our overall composite system, the two subsystems, this relationship should be obeyed, or in other words, T1 is equal to T2. Okay? And so really by doing this analysis, what this tells us is that equilibrium is achieved. We know equilibrium is achieved when the entropy, total entropy, is maximized. And so essentially, the number of microstates in our combined system is maximized when the temperatures of the two subsystems are equal. Right? Or in other words, or this is the definition of thermal equilibrium. Right? And so, here, so just remember what we were doing. We were just trying to find the value of U1 that maximized, that had the highest probability. And that value when that value of U1 occurs, that occurs when the temperatures of system 1 and system 2 are equal. Other values of U1 can occur. They're possible. But compared to the most probable U1 value, the other U1 values have small probabilities. Okay? All right, so here we, derived the sort of relationship for thermal equilibrium. But, we could also similarly derive other sorts of equilibrium relationships. Right? Specifically, we could show the following. So it can show that at equilibrium, the following are true. The two pressures of the subsystems are equal, and the two chemical potentials of the subsystems are equal. All right? And so, this one would be mechanical equilibrium, and this one would be chemical equilibrium. Right? And so, these sorts of relationships are necessary criteria that need to be satisfied in order for a system to reach equilibrium. All right, so, there we came up with some rigorous definitions for what equilibrium is. There's also another sort of approach that we could take towards defining equilibrium. And specifically, we could define equilibrium like this. And so when we put the two subsystems together, subsystems 1 and 2, they could interact in some way. And we could say that through their interactions, what they're doing is they're removing an internal constraint. An internal constraint from system. So if we go back to this sort of picture, when the two subsystems were isolated, their energies were basically constant. But here, when we put them together, that allows the energy of subsystem 1 and the energy of subsystem 2 to actually continuously fluctuate back and forth. Right? So that allows the energy to kind of change over some range of values. And so essentially, the overall entropy of the combined system we could say that it's greater than, or at least equal to, the overall entropy of a system which has some sort of internal constraint. Right? So if you remove this constraint, then your entropy is going to be greater. All right, and in fact, that's a alternative but equivalent definition of the second law of thermodynamics. Okay? Such that spontaneous processes in isolated systems that result in the removal of an internal constraint. Removal of internal constraint can only increase entropy. Right? So this is another way to define the second law of thermodynamics.